Um, Welcome back, everyone. There are a few new faces here, so let's take time. Let's take 5 minutes to recap our general setting. We were basically saying, say that we're Amazon. We have lots and lots. Say that we have the best, I/O in the world. We have lots and lots of clean. We've seen in previous transactions data that we can turn into, perfectly clean valuations. Um, Even in this case, and this, taking this frequentist approach that there really is, the stationary distribution of valuations in the population, from which we see, the bidders that we see are essentially samples from that. Even in that case, it is unreasonable. One could claim it is unreasonable to think that we would know this distribution precisely. At most, we will have seen many, many samples from this distribution, and we said that, we take the very, qualitative point of view of computer science, saying polynomially many samples in the number of buyers, the number of items, et cetera, and all the parameters of the problem. That's a reasonable amount of samples. If we can get a good result that uses these number of samples, that's great. Exponentially is too many. And we said we have one seller, n item for sales, m potential buyers. Each valuation is independent, so i's valuation for item j is drawn from independently from a distribution Vij supported on 0h. Valuations are additive across items, and the seller wishes to find an IR and IC mechanism that yields good revenue and expectation over this distribution. We said the standard Bayesian settings assume complete knowledge of this underlying distribution, and we're interested in asking what can we do if we have access to only polynomially many samples from this distribution. But our benchmark, we're making it harder on ourselves. We're leaving the benchmark to be the optimal auction if we had precise knowledge of this distribution. So this is the drawing for the illustration for Bayesian auction design. The seller is giving distribution from which required types valuations are drawn, but does not know the realizations, does not know the realized values of the buyers that they will face in a second. And the goal is to find a truthful auction maximizing the revenue and expectation over this distribution. So there's a distribution, goes into this, algorithm machine that designs auctions. Out goes the rule of the auction that should perform well over this distribution. We said this empirical auction design, automated auction design, revenue maximization for samples. There are many, many names for this. The differences are the things in green. So the seller is given polynomially many samples from this distribution, does not know either the distribution or the realizations of the buyer that will come in a second to participate in the mechanism. And the goal remains the same over the, it should maximize the revenue and expectation over the unknown distribution. Maximize comes with an asterisk up to an additive epsilon and with high probability.
Can I quick question about the peak constraint?
Yeah.
They don't know the distribution.
We'll get to it.
Okay.
We'll get to it. I promised yesterday we'll get to it. Yeah. Okay, and as we said, the naive approach might be perform Bayesian optimization with respect to this empirical distribution, the uniform distribution over the multi-set of samples that we've seen so far. Hope that this turns well. The potential problem is overfitting. If you're have many, many degrees of freedom in choosing the auction, you might overfit to specific nuances in the empirical distribution that do not exist in the true distribution. So let me jump. So the high-level recap, we talked yesterday about taking a parametric approach. Assume that you're optimized, assume that um, actually not, this- we said, you know, if we know that we're gonna get a good result by optimizing over a family of structures that are a family of auctions that are well structured, because of Moshe's beautiful result that says that if we maximize over separate selling and bundling mechanisms, you know, the best out of all of these is going to guarantee a 1/6 fraction of the optimal revenue. If we optimize, give me 1 second please, optimize over this family of mechanisms, for example, we proved that the pseudo dimension, you know, one example that we use for a learning theoretic dimension of the class is low enough to promise that there will be no overfitting. So we said that the general, you know, kind of two-step dance in getting empirical revenue maximization guarantees was first understand the structure of good revenue auctions. This could be Meyerson for the single parameter case, or one of many beautiful papers that show constant factor approximations for the revenue in the multi-item case, and then use these insights to say, well, it's actually, if we, you know, it's fine to restrict ourselves to maximizing over a low-dimensional set of such auctions, and there will be no overfitting. And as we said, you know, the single item, or more generally single parameter, Meyerson completely solved the Bayesian problem. We have a variety of papers that transform these structural insights into up to epsilon maximization from samples. Multi-item, multi-parameter, we have beautiful papers. This is Hart-Rennie. This is the one Sergio spoke about 2 days ago, the 70% or 60, 72, 73, 78 is the upper bound. Yeah, the 72 or 3, I don't remember, yeah. Percent of the optimal revenue, and you know, this is Moshe's paper, and there are many other beautiful papers here. And these are papers that, you know, painstakingly took these structural insights and using learning theoretic dimensionality arguments showed that if you optimize over these classes, or, you know, versions of these classes, you will not get overfit. And we finished last time by noting that while, you know, each of these papers is really a technical marvel, as computer scientists, we need to, you know, for the econ students in the audience, this sentence is not for you, but as computer scientists, we need to remember that if, you know, solving a problem up to a factor of 50, when we're talking about runtime, even when we're talking about communication complexity, that's completely acceptable. Solving a problem up to a factor of 50 when we're talking about revenue is not always as acceptable. You know, you're going to go to the Machne Yehuda market tomorrow for a tour. You can check, you know, go to a random person at a stall, ask them, you know, I have a wonderful method for you to make sure that you get at least 1/50 of the optimal revenue that you might get otherwise. See if they take it or not. So it's and this is, you know, I'm saying this a bit tongue in cheek, but it's you know, these are not unimportant papers. These are papers that gave us a lot of structural insight and mathematical insight that then translated into beautiful things. So I'm not saying these papers are not important in any way, but all I'm saying is that computer science has a tendency of thinking that if in a certain setting they solve a problem up to a certain factor, a constant factor, that problem is solved. And I would like to urge you to think in terms of revenue that should not be the end of the road for these problems. It is worth to continue to think about them even after we have a constant factor solution. So in that vein, if we want up to epsilon, you can think about 99% of the optimal revenue. As Sergio told us, even for one buyer, 2 items IID, we have no idea what optimal auctions look like. What you know, up to epsilon optimal auctions look like. So this two-step dance. We're kind of stuck in the first step. And we said, you know, because we're stuck in the first step, what's the point in trying to complete the dance? You know, what's the point of trying to solve the problem for samples when we don't know how to solve the Bayesian problem? And I finished by saying that if we would like to make some progress here, if that's possible, we would need approaches that do not rely on the auction structure. And that's what we're going to talk about today. I'm going to call this non-parametric learning. So obviously what we're going to get here will not be, you know, a result that says here is an efficient algorithm, that computationally efficient algorithm that from samples will, you know, give you an up to epsilon revenue maximizing algorithm, if revenue maximizing auction. If it were, it would solve this, you know, as an intermediary problem, and you know, whatever I'm going to show you today will not be solving this as an intermediate problem. And we can't really hope for something here that gives us too much structure, again, because this will solve, you know, questions that are open here, and I'm going to tell you some stuff about this, you know, corner of this table today. I'm not going to tell you anything new about this table, the corner of the table. This was, you know, so the question is, what can we do? So first of all, I'm going to say that we'll already step a bit out of this paradigm that we've been using so far. There will be some modifications, you know. We will be using Bayesian optimization as kind of a black box, even though we don't know how to do this optimization for multiple items. But there will be some modifications here. There will also be some modifications from the samples into what we feed into the Bayesian optimization problem. So there will be a few changes. Just to remind, M buyers, N items, valuation support non-zero H, and here's a theorem by Matt Weinberg, who's a wonderful computer scientist at Princeton, and myself. I'm going to say, then we're going to parse it. It's going to take us a few minutes to parse this statement. So for every epsilon and delta, the sample complexity of learning with probability 1 minus delta in IR and epsilon IC auction that maximizes revenue among all IR and epsilon IC auctions, maximizes revenue up to an additive epsilon, is polynomial in everything that our results from yesterday were polynomial. So a few explanations are in order. So first of all, we defined
Polynomial in H or in log H?
In H. Even what we did yesterday was polynomial in H. The sample size had a H squared in it. That's what we did. Bayesian incentive compatibility, we defined, we said, you know, my expected payment as a buyer in expectation over everyone bids, if I bid truthfully, is at least as high as my expected, sorry, I shouldn't have said payment, my expected utility in expectation over everyone bids when I bid truthfully is at least as high as my expected utility and expectation over everyone else's bids if I bid something else. Epsilon IC is exactly this, up to an epsilon. Maybe you lose, maybe you might be able to gain a cent by, you know, by trying to explore other bidding options.
So the difference between this theorem and the one we've seen yesterday is that here we don't assume anything about the class of mechanisms.
Yes, but let me get to it. There are a few more qualifications to say here. The second thing is that this, I'm going to show you the analysis for epsilon BIC. There's a similar analysis for DSIC. The caveat there, this is the reason I'm showing you epsilon BIC, is that here, the among all such auctions, we only know how to find an IR, an epsilon DSIC auction that maximizes revenue among all IR and precisely DSIC auctions. Here in the theorem, as I've said to you, the epsilon IC is both here and here. So this is why I'm showing this to you, but we know how to do variants of this analysis for other IC notions. I would like to stress that this is for a result for a computationally unbounded settler. This does not say there exists an efficient algorithm, a computationally efficient algorithm, that if you feed into it so many samples, it will output an auction that, you know, maximizes revenue up to, et cetera, et cetera, et cetera. If in some cases, in cases in which we know how to do the Bayesian maximization computationally efficiently, this will transfer into here as well. But in cases in which we don't know how to do the Bayesian optimization computationally efficiently, neither will this. So you should read this general theorem as an information theoretic result, saying in polynomially many samples contain in them enough information in order to identify a very good auction. If you would have thought about, you know, a single sample, even if you're unbounded computationally, a single sample cannot possibly contain within it enough information to uniquely identify, you know, even uniquely identifying the mathematical sense, an auction that maximizes revenue up to an epsilon. So in a precise sense, and we'll get to a you know, more general version of this theorem in a few slides, the way that you should read this theorem is saying, if you're willing to pay an epsilon in incentive compatibility, samples aren't really that much of an issue. Whatever you can do with Bayesian optimization, if you can do that efficiently, you can do this efficiently. If you can do that inefficiently, then you can do this inefficiently. The third point, and this is getting to what you asked about, is the proof assumes nothing regarding the structure or dimensionality of optimal or even approximately optimal, you know, auctions. This is the main difference between this and everything we've seen so far, and really most of the literature that did that two-step dance, and I'm going to show you how we accomplish that. Moshe had his hand up
Is it a good
first.
time to bug you about the big thing, or wait?
Wait till after I show you the algorithm and everything.
So before that, conceptually, how should I think
Okay,
about
so-
big when they
Okay,
don't know
so
the distribution?
conceptually you can think about it in two ways, or three ways. But you know, I don't have a perfect answer to this. One of them is sometimes the buyers know things that you don't. If you're in that kind of market, then you know they know whether it's big or a phone big or whatever. You know, that obviously, you know, that's an answer for specific markets. The second thing is you can think about, you know, if your procedure for finding this auction is publicly available, then they can be convinced as much as you can that it's epsilon BAC. The third one, which is I think the best answer I can give you, is that, as I said, this is not evenly a computationally bound result. This is a result about, do polynomially many samples carry or do not carry enough information to do this? What the buyers know, you know, depend on the specific market,
The
etc.
epsilon BIC is
Mhm.
only with probability 1 minus delta, only if the sample is kind of good, or
With it, you know, with probability delta, maybe you only, you know, if it's a bell curve, say centered around 100, you know, with variance 5, with probability 0, you're only going to get samples that are a million,
right. And then will it be epsilon big or not?
Let me think about this.
We can take it off.
No, it will not. It will again, you know, I don't care which equilibrium they play in this. So you know, with probability 2 to the minus 100, I know, I don't know, the sun explodes tomorrow. I don't know, whatever. You know, so it's, yeah.
So I was gonna ask if you know which of these caveats,
Mhm.
like one minus delta,
Mhm.
epsilon big, are
Mhm.
really necessary.
Okay,
for this
so
result?
as we've discussed yesterday, you know, maximized revenue up to epsilon is needed because you don't see the perfect distribution. You will never learn the perfect distribution from polynomially many
That's not
samples.
epsilon big though.
Give me a second, give me a second. Also, as discussed yesterday, 1 minus delta, as also explained today, with probability delta, you will get very, very unrepresentative sample. No matter what you do, there is a positive probability that you will get exceedingly non-representative samples. So this is unavoidable. The epsilon BIC is an open question. There is hope there, but there seem to be several obstacles. This you know, various people after, actually it's a funny story. The story after this, we spent more time, Matt and myself, trying to get rid of the epsilon after proving this than we spent proving this. At some point, you know, we spent a lot of time getting rid of this. At some point, we, you know, started telling people about this result, but we said, you know, we're stuck with the epsilon, and people were very excited about this result. And, you know, it got into Fox, eventually got into the Journal of the ACM. And it's actually a nice story to, you know, students out there. Sometimes other people appreciate your results much more than, you know, you get stuck on some corner thing that you really hope to get rid of, and actually it doesn't bother people as much. So it's there seem to be several obstacles on the way to this. Several other papers tried to tackle this. All the generalizations that I know of this result to weak correlations and to other settings, et cetera, all of them have this epsilon. No one knows how to get around it.
Okay, and you also mentioned.
I'll show you even some, yeah, sorry, we'll discuss this later, yeah.
You also mentioned the DSIC.
So DSIC, what we can do is get, it's a virtually the same argument. We can get an IR and epsilon DSIC auction that maximize revenue among all IR and DSIC auctions. This is also an answer to you, Moshe. So here you're paying an epsilon in incentive compatibility while not relaxing the benchmark as well. That gets rid of many of these questions.
So you try to get rid of the epsilon, eventually you got rid of the b.
No, it's the same argument. We knew we could do both of these to begin with. We liked the fact that if we're, you know, making it easier for us here, we should make it harder for us here in the same way. That's why the main theorem is weak. Also, you know, in the setting of samples, you know, it is a more complicated discussion, but generally speaking, BIC, when BIC is superior to DSIC, there are a lot of arguments to opting for BIC. I think that, you know, the literature, I'm actually curious to think what you think about this, Eric, but I think that there are a lot of papers that insist on DSIC rather than BIC because, I don't know, because other people do this, because they like this, because this is easier to analyze. I actually don't think there's that much wrong with the BIC auctions. Maybe you'll completely disagree with me. I think that if we're making assumptions about priors, then let's make assumptions about priors.
If you think of the buyers themselves, the demands on them are several orders of magnitude bigger if they have to
That is correct.
worry about.
That is correct. I'm not saying it's not interesting. All I'm saying is that in settings with a gap, my inclination would be to be more interested in both. But you know, if you had me, you know, if you told me in some setting you could get $1 using BSEC mechanisms or $1 million using a BIC mechanism, I would be intrigued about the $1 million BIC mechanism as well. You might disagree.
In private values models,
Mhm.
the two are interchangeable.
Yeah, that is true. Yeah.
And one last question.
Mm-hmm.
I wonder about the last point here,
Mm-hmm.
and I'm curious to hear your thoughts about it.
Mhm.
Were you surprised? Do you see it as a feature, as a strength of
So,
your
so
result?
I see it as the only way to get this result. I see it as a feature. Give me 2 slides and I'll tell you why I see this as a feature. Okay. Last thing, I'm
I have a
giving
question,
this.
can I
Yeah.
ask a
Sorry. Yeah.
Yeah. So, I feel like here two things are conflated. One is that we relax the IC.
Mhm.
The other thing is that we get more revenue because we relax the IC.
So as I said, if I relax BIC
Yeah,
here
I'm on
and
both
in the
sides.
benchmark, then I think
But it kind of means that if you're willing, the more you're willing to sacrifice of the BIC, the easier it is to get an optimal option in the larger family of options, because the probability delta will increase also.
this
Or
does not have
one
anything
might
to do with delta. No. What I relax is that my benchmark is the optimal epsilon BIC auction.
No, but what I'm saying is, like, there's like a set of BIC options, and the set of epsilon BIC is like larger,
Yeah.
and in this larger set you might get more revenue.
Yeah, but I think I'm comparing apples to apples and oranges to oranges here, right? The original question, without the epsilon was, in the set of BIC auctions, can you get something that maximizes revenue up to an additive epsilon? Here we're answering the question, in the set of epsilon BIC auctions, can you get an auction from that set that maximizes revenue up to an additive epsilon? So I think I'm not cheating on this.
Sure, okay, but what if the revenue you can get by relaxing BIC by epsilon is higher than epsilon, and then so can you win in revenue here?
No, but either way, you should get epsilon close to the optimal. If
No, but
the
then-
optimal is bigger, you should get
What I'm saying is the
epsilon.
optimal changes, right?
Yeah, but what you should get changes as well. What this auction should achieve changes with the optimal, right? Because it's this auction that we find should get whatever the optimal gets minus epsilon. So if the optimal grows, what this auction gets
My
also
point is,
grows.
let's say the optimal gives you 2,
Okay.
and you have an epsilon of 0.1.
Okay.
And then, okay, up to an epsilon meaning like you wish to get 1.9.
Yeah. Mhm.
But what I'm saying is once you relax by epsilon, make it the optimal revenue of the optimal mechanism, that is epsilon BIC,
Mhm.
0.1 BIC, is now 2.2.
Yeah. So what
then
you
you
should
get
get is
2.1.
2.1. Yeah. I agree.
And that's higher.
Yeah.
Okay. That's what I said, like it's
Okay.
conflating these two things. in a sense. So maybe you could ask what's the optimal epsilon or something like that.
I agree with everything you said except the conflation part.
No, but you can say, okay, I'm fine with epsilon 0.1, but what if I look at epsilon from 0 to 0.1, and now I ask, well, I decrease by an additive, right? By an additive epsilon, but I also get some more mechanisms, more revenue, so
Mhm.
where's the optimum there?
Okay, so I would have loved to be able to answer either of these partial questions. I don't think that this is cheating in the sense that I'm, injecting welfare into that I'm somehow injecting welfare into the market in order for myself to be able to extract that. I don't think it's that, but I agree with you that there are many other variants here, intermediate problems, you change this and not that one might want to answer.
Maybe a related way to put it, do we know that epsilon big mechanisms are not much stronger than big mechanisms in terms of revenue? Like,
Yes,
is there a bound that says you don't gain more than epsilon? or
you
something?
don't get more than a square root of epsilon. We'll
Oh,
get to that.
okay.
Yeah, there is
So-
such a bound.
So you cannot get to 2.1 in example.
Depending on epsilon. Epsilon
No.
0.1,
Yeah,
so
It will always be less than 2 there, basically.
no, you might gain the square root of epsilon. If epsilon is 0.1,
So it's minus epsilon plus square root of epsilon.
yeah.
You're
Which is
talking
less
now
than
about the benchmark?
No, square root of epsilon is bigger than epsilon.
Yeah, true.
It's less than 1.
Yeah, yeah.
So-
Yeah. More, but
Yeah.
okay.
Sorry, yeah.
That discussion was about the benchmark, if I understand
The
correctly?
benchmark. It was the question about the optimal epsilon BIC versus the optimal epsilon BIC auction. We know that they are not very far apart. Yeah. Last thing I want to say that I'm showing you this for additive valuation. This is actually not critical here. You can generalize far, far beyond that. You can even do externalities and you know, some other stuff. So this, in terms of what we do need is independence. The way that the values of the items accumulate to make your total value for a bundle, actually there's a lot of,
Up to what?
there's a full slide, but it's you can do many things. You can do public projects, you can do externalities, you can do you can even do some super additive stuff. You can do a lot of stuff. Okay. In particular for special cases, in the single buyer case, we actually get precise incentive compatibility from the same argument. This should be compared with a paper by Noam and co-authors Shadin Dohmi and Lihan that says that if you have any correlations, even in the single buyer case, you cannot get any constant fraction even of the optimal revenue, let alone let alone up to an epsilon. You know, so that's this is a stark reminder of what Serge talked about, which is that correlations kill many things. Second thing is single item, many buyers. We get DSIC like Meyerson gets, and we also get computational efficiency. So in this case, if you compare to the parametric approaches we talked about, it was a corner of the table that was around here. Even in these data, we basically, up to the precise polynomials, and the precise polynomials are important, you know, I'll give you that, we actually qualitatively manage all of the settings that this box manage. So this is you know, the agnosticism to the structure of the auction doesn't hurt us, at least qualitatively, even in the setting in which we know what the structure of the optimal auction is. So I'll drive this result, and I think this will be the answer to your question. So we're going to assume access to an oracle. Oracle is a computer science way of saying black box. That can solve the Bayesian revenue maximization problem for explicitly given discrete distribution, but assumes nothing about the structure of its output. We're going to assume nothing about the structure of its output, and we're going to construct our learning algorithm, saying algorithm in parentheses because this black box might not be computationally efficient, so neither will algorithm. We'll construct it around this algorithm. In fact, what we prove is what computer scientists might call the black box reduction, what we might think about, what economists might call black box transformation, converting middle column results in the table that I showed you, you know, Bayesian auction design, to right column results in the table that I showed you. So our meta theorem, if you wish, is the following. For any percent at C, think about C equals 1 for a second, 100%. If there exists an algorithm for 100% or you know, 1/6 revenue maximization given an explicitly specified finite distribution, then for every epsilon and delta there exists an as computationally efficient algorithm. If you know how to do this computationally efficient, you would know how to do this as well. For an epsilon less than C% revenue maximization with probability 1 minus delta given polynomially many samples from the underlying not necessarily finite distribution. So if you know computationally efficiently in some, you know, multi-item setting to get a 1/6 revenue efficiently, we give you an algorithm for samples that using polynomially many samples gets you the same minus an epsilon. If in a single item case you know how to do this efficiently with 100%, we give you 100% minus epsilon from samples. If in the multi-item setting, you know how to non-computationally efficiently get 100% revenue maximizations. You always do, right? Non-computationally efficiently, if you see the entire distribution, there is an exponential size or a huge or infinite size or whatever linear program that will get you that, then we can convert that into an information theoretic existence result that says polynomially many samples convey enough information to information theoretically identify an auction, which is what I showed you later. And the two caveats are loses and epsilon incentive compatibility here compared to here. But if you give me,
finite distribution,
sorry, here,
finite distribution.
distribution with finite support. So it loses an epsilon here compared to here, except for a single buyer or a single item, there's no loss in incentive compatibility. And a single buyer, you can think about the example I gave yesterday with Apple Music selling a music track. Essentially, they're facing one buyer at a time because they don't have supply constraints. So that is captured by a single buyer. So I'm going to give you an outline of the proof of this. Questions so far? So, Michal, the reason that I find to answer your question, the reason that I find the agnosticity, I'm not sure how, this being agnostic to the structure, I find that as a positive because it gives us this kind of black box, reduction black box information that says, I don't care how this works, I'll give you this. So the overall message of this is basically saying, if you're willing to endure a loss of epsilon in incentive compatibility, you know, modulo all of your rightful comments, Moshe, samples aren't as big of a deal as we thought they were.
So I agree, it's very strong, like having a black box reduction. What I had in mind is the question of whether you could take advantage of the structural properties of the original mechanism in order to improve your method.
So I have not checked, but you know, I said here up to precise polynomials. My hunch is that one of these, you know, that there's a et al. Paper 2019, the one that I had bolded on the further reading slide from yesterday. They for the single item case, they actually pinpoint the precise asymptotic sample complexity. I have not checked, but if you had me guess, they probably have a lower polynomial dependence than we do. Maybe I'm wrong. I don't know. But that would be my hunch. So you know, I do not have reason to believe that you cannot make this polynomial better if you have if you know stuff about the structure of the auction. But in terms of, you know, which settings are possible, which are impossible, this covers quite a lot.
But you know that polynomial dependence on all these parameters is necessary, right?
We know that polynomial dependence on all of these parameters is necessary.
So for example, do you know that you have to be polynomial in H and not in log H?
I believe that we do. I believe that we do, but
Scaling, that should be easy.
yeah, I believe that we do. You know, there's a whole other genre that I mentioned yesterday, but I will not speak about, which is what do you do with unbounded valuations. There, obviously, you don't have dependence on H. There you have to assume various tail conditions, you know, that the tail of the distribution isn't very heavy, et cetera, et cetera. So, you know, that's a different one. So I'm not going into that, obviously, when I'm saying, you know, we need the dependence on H. For arbitrary distributions, I think this is necessary, but, you know, I can check. I believe it is.
Yeah, but my question was more conceptual than really how
Yeah,
the
no,
polynomials
so
change.
conceptually, these are the parameters you should care about, and these are the parameters, you know, this is what we give, this is what we need. Okay,
Can I ask a question?
yeah.
So first, why is there dependence on H? Can it be always normalized? Divide by H or something?
Okay, so one thing here is that we're doing an additive epsilon, not a multiplicative epsilon. Okay? So,
Okay,
so,
yeah, sure.
this answers your
Yes,
question.
yes.
Um,
And I have another one,
Yeah.
so, there exists an algorithm, do we know it?
yeah, as I said, if you give me the thing that does this as a black box, I'm gonna tell you in the next slide what is the algorithm for this.
Yeah, okay.
So we assume an oracle that can do this, and we build stuff around it and get an algorithm that does this.
Can deep learning approaches be considered like a universal algorithm here?
Deep learning, like anything else, is susceptible to overfitting.
Yeah, of course.
There are beautiful papers initiated by my colleague at Harvard, David Parks, in the computer science department, about deep learning of optimal auctions. There are wondrous things there. I don't know, you apply that to many distributions that, took us a long time to do analytically, and you run it, and the structure kind of, jumps at you. I do not know of a theoretical result that says that that would work just anywhere out of the box.
I mean, they have a loss function, and if it's optimized exactly, then it's an exact.
Yeah, no, but the problem with neural networks, you get into local minima, et cetera, et cetera, et cetera. It's
hard to analyze.
it's hard to prove stuff about that. Okay. So here's the learning algorithm outline. It's going to be, deceptively simple. The analysis is going to be the interesting part of the following slide. So assume we have each sample. S samples, what is each sample? Each sample is V11 through VMN. So, for each buyer item combination, a sample from capital V ij. We're gonna start by mixing and matching them and forming capital W11 through capital WMN. These are gonna be, for this you take all of the samples from V11 and you take the empirical distribution over these. Almost, you round down all of these to the nearest multiple of epsilon. This is actually very complicated. Then you construct the product distribution over these. Then you feed it into your optimization oracle. This is my son Shahak when he was half a year old. This is going to be important soon, next to the oracle's temple in Delphi.
Can you explain what it means, W11 equals unif something?
So it's the uniform distribution over this multiset.
So you form new random variable?
I form a distribution, random variable if you wish, that is the uniform distribution over all of the samples I get from buyer 1, item 1, but I round down each of them to a multiple of epsilon. This will be important for the analysis, the rounding down.
It's just discretization.
Sorry?
Just discretization.
Just or not just is in the eye of the beholder, but discretization. We'll see later that this actually is crucial.
So what is the little epsilon doing there?
This is rounding down to the nearest multiple of epsilon.
Okay.
Sorry, that's so if this is 500 epsilon plus 1/2 epsilon, you round it down to 500 epsilon. So you feed this into the optimization oracle, gives you an auction mu. I have no idea what the structure of mu is. Mu is an auction that has been optimized to work well on bids that are multiples of epsilon. That's all the inputs that it saw. So I'm gonna massage it into my final output. So the final output, what it is going to do is it's going to get bids, round all of them down to the nearest multiple of epsilon. That's the loss in semi-compatibility. And then it's going to pass them to this auction. This is my learning algorithm.
So it's empirical optimization of left.
Up to rounding of epsilon. This rounding you'll see in the next slide, is what drives all of our analysis.
You may be losing incentive compatibility, but up to epsilon.
Up to epsilon, I'm losing incentive compatibility. That's exactly the reason we had epsilon BAC. I'd like to remind you two things. First of all, we know nothing about the structure of the output of the oracle, much like the syllables uttered by Shahak when he was half-year-old. I told you that would be important. And we do know that the optimal auctions, even near optimal auctions, have very high dimensionality. So, you know, the main thing I have to show you is why is there no overfitting. And one hint here to people who are familiar with the literature on model misspecification, on people with misspecified priors, you can think about this as a deliberately introduced, very controlled model misspecification so that our statistical analysis will be able to rule out overfitting. If what I just said meant nothing to you, you can ignore it. We'll give more details in the next slide. So
So then I would it be fair to say that all this slide says, which is a lot, is that if you take the empirical distribution and feed it to your algorithm, it works.
if you take the empirical distribution rounded down
Yeah,
to
yeah,
multiples
rounded
of
up.
epsilon, and when I say empirical distribution, this is the reproductized empirical distribution, right? It's not the uniform distribution over these tuples. It's the product of the uniform distributions for each of these separately.
Because
Okay.
it's independent.
This is, again, very, very important. The reason it will work is independence. But yes, usually when we say empirical distribution, we mean the uniform distribution over these. As we'll see later, usually when you do Chernoff-Hufting or a Zoom or whatever, it's assuming these. We will use a variant of Chernoff-Hufting that's specific for reproductized distributions.
Okay, what happens if you do the traditional thing?
I don't know that it will not overfit. At least the analysis in the next slide that says no overfitting will miserably fail if you do the uniform distribution over this.
It's a very correlated distribution.
It's a very,
uniform over
yeah. So it's, actually that's a good point. Since it's a very correlated distribution, maybe Kramer-McLean will give you, the optimal.
So doing the second line here really was taking advantage of the independence and.
The reproductizing it is what takes advantage of the independence. Okay. So, redrawn this algorithm, you start with this reproductized distribution, feed it into the oracle, out comes an auction, you massage it into an auction that rounds its inputs down and send it to this auction. And instead of thinking about this as drawing and then rounding down, I'm going to think about this as there's the original distribution that we don't know. There is the rounded down to epsilon version of that distribution, and I'm going to think of ourselves as drawing the samples from this distribution. This is the same if you round before or after you draw the sample. This is going to make the analysis easier. And this mu here, I also copied it to here just because it will make the arrows look nicer on this slide. What we do know, this is what the oracle guarantees to us, is that this is both BIC and optimal for this distribution, right? That's the whole purpose of the oracle is it gets the distribution to output something that's BIC and optimal for that distribution. So far it's safe. First thing I want to prove to you is that this is up to order of epsilon. By that I mean some constant times epsilon. It's optimal for this original discretized distribution. So I need to prove to you that mu attains similar expected revenue over, okay, so I'm going to prove to you that mu attains similar expected revenue over this and this. This is going to be the first step. The heart of all of this argument is to say it's enough for me to show you that for S plus 1 to the MNH over epsilon, specific auctions, they attain similar revenue here and here. So I can prove to you that for each of so many auctions, it attains similar expected revenue here and here. By a union bound, whichever of these I happen to have in my hand as mu, it attains similar revenue. So it might seem like I'm lying here. I just told you I have no idea what the structure of this is. Then I'm telling you it's sufficient for me to keep in my mind s plus 1 to the mn h over epsilon auctions. It seems like I'm lying, but this is the heart of the argument. My claim is that this is an upper bound on the number of product distributions I might feed into the oracle. Why? Sorry? So if you think about each of these separately, each wij by itself, it has h over epsilon buckets in the distribution. The support is h over epsilon, plus 1. Forget the plus 1. The support is h over epsilon. Each bucket in the support has between 0 and s samples in it, right? It's a distribution that's constructed from s samples. So a single wij, the number of possible such auctions is s plus 1 to the h over epsilon. That's the number of samples you can, of distributions with support of size h over epsilon that can be constructed from s samples. So the product distribution altogether has, there can be at most that to the m times n different product distributions. Which means that this oracle, whatever it may be, has at most s plus 1 m and h over epsilon outputs, not all together, but over any distribution I might feed into it. Okay, this is the conceptually hardest part in the proof, so do ask if this was not clear. So I'm basically saying this oracle could be crazy, but if I feed into it only product distributions that I've constructed from S samples that are multiples of epsilon, that's the whole point, it will only output so many different auctions because I'm only going to input into it so many different distributions in any possible way. So I want to show that for each of these auctions, I have no idea what they are, right? I don't know how to run the oracle. It might not be computationally efficient, but mathematically they exist. So for each of these auctions, if I show you that except for events that have probability delta over this number, each of these auctions has similar revenue here and here, by a union bound, all of them have similar revenue here and here, and in particular it will mean that any mu that is output has similar revenue here and here, which is what I wanted. So we need to do some kind of Chernoff-Hafting. This will be the failure probability. So number of samples will be about log of 1 over the failure probability. That's the point of Chernoff-Hafting. You need log of 1 over the error. I'm hiding some factors here that don't. So this is kind of weird, right? I mean, the error that the error that we want shrinks as we take more and more samples. Okay, so we need more samples as we take more and more samples. So usually in statistical learning, we have a hypothesis class, and we ask how many samples do we need to, learn stuff well over this class. Here it's not a fixed hypothesis class. The more samples we take, the larger the class we want uniform convergence over is. So it's a race. There is, when we enlarge the class of auctions, we need more samples, and then as we need more samples, we need more auctions, and the question is what wins. And because of this logarithm here, if you do the calculation, you'll see that this grows with s, but moderately enough, so that a polynomial number of samples will give you an equality here. So this is where this diverges from many, many dimensionality arguments and learning algorithms. Okay, so far what did I show you? I showed you that mu attains similar expected revenue, up to an epsilon here and here. This is insufficient to prove that mu is almost optimal for this, right? I've shown you that, if mu gets $100 over this distribution, it will also get, $99 over this distribution. But maybe there is another option, not one of these options that we considered, that gets $1,000 over this distribution, but only $100 over this one. So I showed you that mu gets similar revenue, but maybe here the optimal really is what mu gets. Maybe here the optimal is so much more. So let's consider this hypothetical optimal that is optimal over this distribution. Let's write it here. It's clear, it's completely clear by definition that mu gets at least as much revenue over this distribution than this optimal is. Why? Because mu is optimal for this. I'm going to claim to you that mu gets almost as much revenue as this does here. How am I going to claim this? I'm going to change what I proved to you. I'm not only going to prove to you that mu attains similar revenue here and here. I'm going to prove to you that this hypothetical optimal auction for this rounded product distribution also gets similar revenue here and here. This will actually complete the proof. If the optimal for this attains almost the same revenue here, and the optimal for this attains almost the same revenue here, then we're really done with optimality, not with DIC, but with optimality. And here's the trick, and again, it's a conceptual more than a mathematical trick. This auction, hypothetical optimal auction for this distribution, I can never hope to know what it is. It's a function of the original distribution from which I only see samples. Nonetheless, it is a well-defined mathematical object that is independent of the samples. Therefore, my claim is that when we do this analysis, what we really need is to prove not that the s plus 1 to the m and h over epsilon auctions, all the possible outputs of the oracle, get similar revenue here and here. We need to prove that this plus 1 auctions get similar revenue here and here. What's the plus 1? It's this optimal auction for this that we don't know what it is, but it is a well-defined mathematical object. So it's a plus 1 here, it's a plus 1 here, it's a plus 1 here, but all the argument goes through. Good. So this is, I proved to you this. So this is actually for epsilon optimal. What about epsilon dx? So here, what I need to prove to you is not only that mu has similar revenue here and here. What I want to prove to you, and we're going to go back here, that mu as well as opt not only attain, but think about mu, not only attains similar revenue here and here, it also has similar reduced form here and here. What do I mean by reduced form? I mean all of these random variables, some people call them the reduced form. What are these random variables? All of these expectations, sorry. The expectation when I bid VI in expectation over everyone else's bids, that my utility is better than if I bid VI prime. If I show you, and I would like to remind you that BIC is determined by inequality between these. So if I show you that each of these has similar expectation here and here, then if here there is an inequality between two of these, here the inequality will hold up to an epsilon, which is precisely the meaning of epsilon BIC. So I would like to prove to you that each of these expectations is similar here and here. So these are just more things to add to my union bound. Instead of thinking about one random variable, the revenue per auction, I'm thinking about one plus many more random variables per auctions. This one is the revenue. These are all the variables in the reduced form, right? I, there are m options. Vi, there are h over epsilon options. Vi prime, also h over epsilon options. And where did I cheat? Where's the n coming from?
VI is h over epsilon to the n.
Yeah, Vi is h over epsilon to the n. Thank you. Good. So it's, it's becoming one heck of a union bound. But if we copy this here and copy this here, we'll see that the number of samples, this hypothesis, this grows much bigger now, this set that we want a uniform convergence over. But still, we need S that equals roughly polynomial and stuff times log S. So still the sweet point has S polynomial in everything. So I've proved to you also epsilon BIC. And I will not do this now, but the rounding is more epsilons, but that's it. So let me do talk about 2 points that I glossed over in this proof, which are important to make sure we don't gloss over. So the first one is, you can tell me, well, Yanai, you cheated. In what way did I cheat? You're comparing to this opt. Opt, if it's BIC for this, it's epsilon BIC for this, so this is 2 epsilon BIC for this, so something here gives, and you get more epsilons than you started with. This mu, it had if opt is BIC, this is, epsilon BIC. If op is epsilon BIC, this is 2 epsilon BIC, whatever. You got more epsilons than you started. And here comes what you asked about. There is a beautiful theorem that says you can actually, epsilon BIC and BIC, the maximum revenue is not that far apart. And this is from Rubinstein and Weinberg, goes back to Daskalakis, Weinberg, the roots of this, and this says what you get using BIC, what you can get using BIC auctions and what you can get using epsilon BIC auctions, the difference is at most various stuff times epsilon.
What's
Arbitrary valuation, this is like monotone, all monotone valuation?
No, I think it really is arbitrary.
Arbitrary.
Yeah. Yeah.
What's L?
What is ill? That is a very good question.
Oh, maybe they're between L and H.
Yeah, no, but we didn't need this in our analysis. So I either copied this wrong from their paper or... That's a good question.
By the way, in their paper, it's also the same notation for MN or the other way around?
No, so this is massage from their paper. This is, no, the reason I did M and N was yesterday, all we had was N. We had a single buyer. So I wanted M to be all around. I don't like only using M when there's no N.
Because once you have N for items and M for buyer, then
Yeah.
you're not a computer scientist anymore.
Because computer scientists use N for...
Of course, how can you use N for items and M for
Yeah.
buyers?
To the attention of the Harvard Economics Tenure Committee. No, I'm kidding. Okay, so this is one thing. The second thing is exactly what we talked about earlier. So when I said we're going to do some Chernoff-Höfting thing, let me reuse my illustration from yesterday. I will need, oh, very good. well. Okay, so think about having many, many samples. Each sample is a vector. Standard Chernoff-Hefting tells us that if we take the empirical distribution is what you referred to earlier. You know, we randomize between this and this and this and this, et cetera, et cetera. We take the uniform distribution over the columns, the average is going to be close to the true expectation. The standard Chernoff-Hefting doesn't tell us that if we reproductize things and the uniform distribution over this product distribution is not the uniform distribution over the rows. It's uniform over the column. Sorry, it's uniform over the first row times uniform over the second row times uniform over the third row, etc. It's basically saying pick at uniform
The first component
one component from each column, never two from the same row. Sorry, the other way around. Sorry, it's yeah, one from each. Pick one from each column, never two from the same row. So it's one from each row.
No, to make one from
Sorry, the other way around. One from pick at random one from each row, rather than pick a full column. Sorry. Yeah, very good. I usually draw this with rows. I didn't want to confuse it with columns yesterday and columns now. That's why I said what I said. Okay, so this is a different beast.
Wait, but I have a question about this. When you look at the value of a single sample, the distributions VI, all the different distributions, are they independent? I assume that the valuations themselves are all,
What?
like the rows,
Yes,
the rows are independent also.
items are independent.
The items are. Okay, so standard off-the-shelf Azuma, Chernoff-Hefting, your favorite will not work here. We need something else. Very fortunately, about a year before we wrote a paper, no, it's actually a few more years because 2017 is already the journal version. In a very different context, Yakov Babichenko et al. Proved a very nice Chernoff-Hefting equivalent exactly for reproductized distributions over samples for the independent case. So this exists and this is useful.
So this theorem existed only from 2017? Or
So I think the
2013?
conference version was 2013
No,
or
I
something.
understand, but it's very surprising that
I-
no one looked at this. It seems that
Let's say
every
this.
fundamental-
Let's say this. You know, this paper, which is a beautiful paper, reproved this and didn't know about this. So maybe this paper reproved it from some other paper and they didn't know about. So you know,
From the 80s.
from the 80s and Russian from the 60s. You know, there's a variety of in German from the 30s. You know, there's a variety of you know, I don't mean to disrespect any of these. Both of them. I'm giving you the Babichenko version because I think it's a bit stronger mathematically. So you know, both of these are wondrous papers with beautiful proofs, etc., etc. But it's we have not been able to find earlier versions of this, and this is already in a journal. So some search was done. Also, you know, Yakov Babichenko is a serious guy. He searches a lot before he tries to put something. So I don't know. Maybe Yossi will tell us otherwise, or to my knowledge, this is the first occurrence of this theorem.
Take a picture and ask Nobel.
Go for it.
It looks like related to bootstrap. Because you're sampling from the sample or something.
Maybe, I don't know, not exactly, right? I mean, so, I don't know. Anyway, so this is the other important component. I didn't want to gloss over this, and this is also useful to know. I mean, you know, somehow morally it should be correct, in the sense that, you know, we're even randomizing more here and somehow, you know, not assuming, you know, we're somehow dependent less on the precise order in which we sampled from each coordinate, et cetera, but it's having something morally and knowing that, you know, it was formally proved is two very different things. Okay, so this is what I have to you about the algorithm. Any questions about this before we move on?
Does it relate to the pseudo-dimension result that you showed yesterday? Like like if you think about fixed sample, then the set of mechanisms is maybe like a finite set.
So
like
here,
random?
if you think about fixed sample size, the set is a finite set. So, you know, most of the results that you know in learning theory somehow make use of something like this. I think the major difference between here and what I showed you in the previous and you know really much of the other literature is we don't limit the outcome. We somehow discretize the inputs in order to be able to count the outputs. And the second thing is that this hypothesis class grows and as we take more and more samples, and luckily there was a sweet spot. So one of the proof ideas, as we said, was a relatively small number of possible oracle inputs. Those are the discretized distribution. So you can think about this as, you know, a deliberately introduced controlled amount of model misspecification, and it comes at a fairly moderate price, which is epsilon IC. You know, the rounding of the samples, you know, at the end of the inputs to the auction, but also of the samples. For one item, we get precise IC computationally efficiently.
Can you give a hint why it's different? Why you
For one sample, it turns out that all of the rounding there, if you take a monotone auction, everything remains monotone, and monotone is IC. So this is, you know, a fluke. For one buyer, there is a known epsilon IC to IC transformation, so not only something, you know, information theoretically telling you you have similar revenue, but there's also, you know, a way to get an epsilon IC auction, turn it into a precisely IC auction, using negligible revenue without requiring any knowledge about the distribution. This is actually a funny story, because this is in a paper by Nina Balkan et al. From 2005. There's a footnote that says if you give everyone a discount, you know, you charge everyone 1 minus epsilon of what you would have charged them otherwise, you know, this fixes something. This is attributed to Noam in a footnote. From reading this, it's not exactly clear that this, you know, this can be, the math is basically, you know, if you look at this deeply enough and you think about this deeply enough, you understand that this is actually a general way to transform epsilon IC mechanism to IC mechanisms. This 2017 Riestad paper in economics is a full paper that's written independently around the same idea that Noam had told someone because he didn't think it was worth writing about. They wrote a footnote about this. This is a Riestad paper centered around the same idea. So it's again an example of when you have an idea, maybe it will be better accepted than you know, just, you know, maybe it will be well enough accepted to be worth more than a footnote, or more than, you know, giving a footnote to someone else's paper. So this is, you know, and so this is also an example of a rare example of not the computer science reproving something in the economics literature, but the other way around. Actually, you know, this is 2017. The rate of econ publications, I cannot rule out that this started before 2005. So I don't know. Yeah, no, but this is a beautiful paper. They also have many other insights. You know, it takes time, even from, you know, this footnote took time for us to realize that this is actually an epsilon IC to IC transformation. They realized many, many more things. I'm not belittling this paper in any way. Just saying that both fields should read each other's literatures. So So this allows us to overcome the model misspecific, and this literature really talks about, you know, overcoming model misspecification. That's the way that this paper is framed. So we introduced model misspecification to get no overfitting, and we can use this to correct it at the end after we're done with the no overfitting. So that's a nice thing. And we do not know, even with follow-up papers and everything, we do not know of a direct path to learning an IC mechanism that is not learn an epsilon IC mechanism and fix the epsilon. So this is, again, only for the one buyer where we know how to fix the epsilon. For more than one buyer, we don't know how to fix the epsilon. We just don't know. I'll tell you about that in a second. There are epsilon IC to IC transformations that you require, I'll talk about this in the next slide. So you can think about this as a, you know, deliberately introduced model misspecification as a tool against overfitting, and if we're lucky enough, we can remove the misspecification at the end. So some further reading, again, there are many, many beautiful papers. This beautiful paper by Russell Young Tsai and Kostis Daskalakis extends our results to allow for certain weak correlation between the V's. Not every correlation, not every weak correlation. Some correlations that come from drawing graphical models for the people familiar with this term. Guo et al., Guo from the same, I think it's the same authors from the 2019 paper I talked about yesterday, plus one additional author. They apply techniques similar to ours, and they say, well, this trick, that what I showed you in the proof, this works not only for auction thefts or profit inequalities, Pandora's problem, and whatnot. What I'm most excited about their paper is that they actually have a lower bound of sample complexity of what you can think about the problem that underlied our analysis and also underlie these, which is learning an epsilon optimal hypothesis over a product distribution as a function of the size of the support of the marginals. If you think about this, this is the inherent problem we solve there. All the rest are you know, bells and whistles. Their lower bound shows that actually our analysis, number of samples that we need, even though we kind of, you know, waved hands and didn't do anything fancy auction theoretically, is tight up to log factors. Log factors meaning, you know, log of n somewhere.
The size of the support of the marginals wasn't at the expression.
H over epsilon. It was poly.
The rounded.
No, but I'm saying this intermediate problem that they give a lower bound is learning an up to epsilon optimal hypothesis over I should have said finite product distribution as a function of the size of the support of the marginals. This is essentially, after discretization, what I showed you how to solve. Right, we had marginals of size h over epsilon. I showed you how to get sample complexity if this is the size of the support. Before that, I told you, you know, the continuous thing we can discretize to h over epsilon, then do our analysis. That's essentially what I told you. So for that specific problem, they show that our analysis is actually tied up to log factors. They actually shave another log somewhere, but it's, you know, so they have a slightly tighter analysis that's also tied up to log factors. Their lower bound implies, the reason I'm excited about this lower bound is because it tells us where we cannot improve in our analysis. So it means that if we would want to improve our sample complexity, the polynomial, this would require either discretizing differently, not to this grid of epsilon of h over epsilon, or have a quantitatively better epsilon IC to IC reduction, one that doesn't lose square root of epsilon, or exploit some currently unknown structure of revenue maximizing multi-item options. So their lower bound tells us what can we improve upon, all the stuff we did around in order to get to the heart of our analysis, which is essentially solving this. Epsilon IC to IC reduction. So Shadin Durmi, Jason Hartline, Bobby Kleinberg, and Rad Niazadeh, they construct an epsilon BIC to BIC reduction, you know, a transformation for arbitrary many items and buyers. These reductions require fresh samples. What do we mean by fresh samples? Each time you run this reduction, you get some epsilon BIC mechanism. If you want to turn it into a BIC mechanism, they know how to do that. It's beautiful. But every time you run the BIC mechanism, for it to be BIC, You need fresh samples that are not the values of the buyers you run this over. You need a continuous stream of fresh samples in order to make the distributions match completely. It's beautiful. They do this using Bernoulli factories. Whoever here is into a probability, it's really a beautiful paper. This is the journal version. The original was stock 17, I believe. They do this in order to preserve welfare between epsilon BIC to BIC. There's a follow-up that also has a similar reduction, similar purpose reduction, fresh samples, et cetera, that approximately preserve revenue, which is what we need here. Either of these requires a number of samples that's polynomial in the size of the type space, which means exponential in the number of items. Okay, the size of the type space here is epsilon, h over epsilon to the n, for example, if you discretize the type, so h over epsilon. So it's polynomial in the size of the type space. At the same time, neither of these assumes independence. So they should somehow be exponential in number of items. Can independence be used to make do with a number of samples that is polynomial in the number of items? I think that's a very interesting question. Can we improve these reductions to somehow leverage independence? It's a hard question. I think it's a very interesting one. Conclusion of further research. So the main takeaway from today was, despite everything I told you yesterday, empirical revenue maximization is actually not harder in a precise sense than Bayesian revenue maximization in many settings, in the sense that any results that holds given full information immediately implies a robust result from samples. That's what I proved to you. That's our meta theory. For many buyers and many items, you pay an epsilon on the incentive compatibility, otherwise you don't even pay that. That's my main message to you from today. The open question is, can you get rid of the epsilon and do a precise BIC, or get rid of the epsilon and do desync that approximates the optimal desync, for the samples. Before we wrap up these 3 hours of yesterday and today, let me just say that there are obviously many things in the literature on mechanism design from samples that we have not talked about. One of them is only a few samples, only 1 sample, only 2 samples, how much you can get. You will obviously not get up to epsilon. Turns out that you can get quite a bit. Even with 1 sample or 2 samples, there are some papers on that, including my own, with Moshe, that specific paper. What about more than 1 seller? We can talk about a 2-sided market with many sellers and many buyers. We know that, good mechanisms there because of the Meyerson Safed-Weight impossibility result. We know that Bayesian mechanisms will give us much more. But we know that mechanisms that are tailored to the distributions will give us much more than, just mechanisms that are not. Can we design such a mechanism only with sample access to the distributions from which the sellers and buyers are drawn from? There are also several papers on that, one of which is, again, my own with Moshe and also Kira Goldner. I think to this point you're still my most frequent co-author among all my co-authors, all my wonderful co-authors. Other objectives, so we talked about revenue, you can talk about welfare, you can talk about other objectives to, design for. And many more things. There are also many beautiful connections. There are connections between selling at 1 sample and the Bulow-Klemperer theorem. Many other beautiful things that we simply could not cover in 3 hours. These are many beautiful papers, but there also is much more to be done. Thank you so much. Yeah.
On the previous slide.
Yes.
Other objectives.
Mm-hmm.
Are we to interpret from that if you did have other objectives, such as welfare
No, the things we have not discussed.
in these lectures, but
Mhm.
has no one discussed them?
No, we have not discussed, many other people have discussed.
Okay, so what is the answer for other objectives?
So, welfare, the settings that I know, welfare is easier than revenue. For some settings, we know only how to do welfare. Two-sided market, many sellers, many buyers, for example, we know how to do welfare. I've not seen anyone take a look at the designer wants to pocket some money because, wants it not to be budget balanced. They want to charge the sellers more than they give the buyers. I've not seen that, for example. You can certainly look into that.
But
So-
for welfare, you don't even need.
Yeah, but this
No,
setting
this-
is trivial.
no, no.
Like, adding
For-
into
for-
our-
for-
trivial.
No,
You can get the basic.
for,
If you don't care about computational issues, you don't need distributional information at all for welfare.
no, but in two-sided markets, for example, you
Yeah,
can.
no, but if you don't go, if we don't go to two-sided markets,
Mhm.
we just have one seller.
But
then
computational
up
issues.
to computational
No, but I
issues-
think computational issues are important. The whole point of this paper is you have some epsilon BIC mechanism. You want to get almost the same welfare of this mechanism in a BIC mechanism, but you have a mechanism in your hand.
But
No.
for welfare, you can do VCG in one-sided market.
Uh,
That's the problem.
A VCG is you cannot always computationally do that.
No, but this setting is additive. He was asking about this setting.
Yeah.
Just additive.
This specific set,
It's very easy.
For others,
You run second price for each item, and that's it.
this specific setting, yes. This specific setting,
But
yes.
if you go beyond additive, then computationally you're in trouble.
Right, but
Yeah.
how is it related to sample? We don't need samples to do VCG.
No, but say that you, no, but again, VC,
No, I
The
think
problem
for-
there is computational, but
Yeah.
it's not the problem of
I
information.
think it's mainly relevant for two-sided markets perhaps.
perhaps. Anyway, read the motivation for this paper. But it's that paper convinced me when I read it. I cannot this time in the morning reconstruct what happened there. But it's so the settings I know welfare is easier. I could also think about various other objectives. Revenue subject to fairness. Some combination of revenue and welfare, I don't know. Generally, so I've not seen other objectives except for welfare and revenue. You can certainly think about that.
But for two-sided markets anyway, it's mainly either welfare or gainful trade, right? It's not revenue
You
per
can
se.
think about you're an intermediary, and you live off the difference between what you got from the sellers and what you pay the buyers. What the buyers paid and what you paid the sellers. You live off that. You can think about, you're eBay. You want to maximize your revenue. I don't know. You can think about these things. I haven't seen, I'm not talking about specific paper. You can ask that question. So it's, hypothetically speaking about other objectives. Again, not speaking about any specific paper, but I could certainly imagine the question. Especially now, you're Uber, you're matching
Yeah, no, but
drivers and riders.
I'm
You
trying
live off the
more
difference between.
to think about how to relate your analysis to existing
Gotcha.
existing objectives.
Okay, no, so think about Uber, for example. You're Uber, you want to maximize revenue. What does maximizing revenue mean? You live off the difference between what the buyers pay and what you pay the drivers. You want to design a market based on, sample information about willingness to pay and willingness to receive. You can certainly ask that question. Yeah. Does that answer the? Okay, so here in a greater way, things I've not discussed. Each of these I wrote because someone did something about this. I tried to phrase this in the most general way to encourage thought. So when I wrote other objectives, I meant some people did welfare. Maybe you can think about also other things. Great, thank you.